Hello, dear colleagues. At first, I would like to introduce myself. My name is Kristyna Vopatova, and I study at the Department of Steel and Timber Structures at the Czech Technical University in Prague. In the next few minutes, I'm about to describe you my research, which is the design of steel to timber bolted joints. This presentation consists of these four parts. In the beginning, I will describe the current practice. In the second part of the talk, I will focus on our experiments. Then I will move on to the problematics of numerical model validation, and at the very end of the presentation, I will demonstrate some of our conclusions. As I said, I focus on the resistance of timber joints with one inserted steel plate connected by bolts. In the Czech Republic, dozens of similar connections have been built. Mostly they are used for large span structures, bridges, or lookout towers. These pictures show some examples. The tensile test of steel to timber joints were performed. Here you can see the layout of the sample number 1. Each sample consists of an inserted steel plate, which is 6 mm wide, placed in the middle of a 120 mm wide timber element. In total, we tested 8 different configurations. The sample's configurations and their geometry vary in the type of timber used, the size of bolts, the number of bolts, and their pitch. Timber strength class C24 is a ground timber, and timber class GL24H is a glued laminated timber. The dimensions of the steel plate and the timber element were same for all the samples. I think that the most exciting part is when these joints fail. In studies by Johansson, there are 3 different ways how they fail, with a difference in the number of plastic deformations formed. In the left figure, these 3 types of failures are shown. Johansson's theory also relies on the design procedures outlined in Eurocode 5. As the main criterion for the evaluation, the mutual displacement of measured points 1 and 2 was chosen. Measuring points 1 and 2 are situated at the beginning of the timber element and at the end of the notch. See the figure on the right. In this picture on the left, you can see all 8 samples after the test, and the whole experimental setup is on the right. For example, sample number 2 has a long crack all along the sample. Sample number 4, 6, and 7 have some small cracks, and sample number 5 has almost no visible cracks. The whole experimental setup before the beginning of the test is on the right. The picture on the left shows the points of measurements. The measurements were done with track sensors. As I mentioned, the samples might fail by many different ways. An interesting failure occurred happened on the sample number 7, which you can see on the figure on the right. These figures show the displacement of sample number 5 and sample number 7. Figure A shows the displacements of the piston. Figure B measured point 1, figure C, measured point 2, and figure D, the difference between them. The measured values for all test specimens are given in this table. It is important to mention that some complications occurred with sample 1 and 3 during the test experiments. The numerical model was created in Abacus software using the finite element method. The interactions between elements was defined by contact bonds. Models of experimental samples were created in the software to simulate the load action on the samples during the test. In the figures, you can see also contact bonds and coupling for entering the actual force. The material properties of the isotropic material were assigned to the steel sheet and bolts. Timber was modeled as an orthotropic elastic material. The linear material model of the timber defines 9 independent elastic constants: Young's modulus of elasticity, shear modulus, and Poisson's coefficient of transverse deformation. In figures on this slide, the validation of the numerical model is shown graphically for test specimens 5 and 7. For these figures, it can be seen that the numerical model is in good agreement with the course of the experiments. The validation of all 8 samples is numerically expressed in this table, where the data on the relative displacement of measured points 1 and 2 according to the numerical model, and the ratio of the displacement between the numerical model and the experiment. The most significant result is the average value of the agreement. The deviation is only 19%, and that is really good, because when taken into consideration that for timber a deviation of up to 30% is considered as acceptable. Experimental and numerical studies were performed and presented. The numerical model gives a very good result with an average deviation of 19%. The numerical model reliably describes the behavior of the solved joint, even though the simplification was introduced in defining material properties and boundary conditions. The analytical model provides conservative results, and all the results of the study combined show that timber joints with steel plates may ensure reliable transmission of internal forces and high load-bearing capacity when the design procedures prescribed by the standard are followed. Currently, we are working on a numerical model in Abacus software using the finite element method, considering plastic deformation and failure mode. Also, we are focusing on the analysis of the steel-to-timber bolted joints during fire. Those fire experiments were also already done. Our final goal is to have one integrated model that could simulate steel-to-timber bolted joints under the tensile and during fire at the same time. If you have any questions, do not hesitate to send me an email. Thank you very much for your attention.